Alright, so now we are ready to study the simple pendulum. Okay, and our goal is to show that under certain conditions the motion of a simple pendulum is simple harmonic. Alright, so now here's the deal. A simple pendulum is essentially a mass attached to a string of length L, and you just move this mass to to one side by some angle theta, and you let go of this mass, and we know that this mass is going to move back and forth. We know that it's going to oscillate back and forth. So the motion is going to be periodic for any angle theta. Okay, assuming that there are no frictional forces, it'll keep on doing this forever and ever. However, we are interested in the simple harmonic part of this motion. So when is this motion simple harmonic? And here's the statement. We'll make the statement. Okay, when theta is small, which means the initial angle that we give it is small, such that sine of theta is approximately equal to theta. Okay, the motion of the simple pendulum is simple harmonic. Okay, and we'll show you. We'll obtain an equation. We'll show that the displacement is going to have, there is going to be, the acceleration is going to be linearly dependent on the distance traveled. Okay, so just to give you a quick idea about the sine of theta, if you take your calculator and find the sine of 10 degrees. Okay, if you look at 10 degrees in radians, 10 degrees is equal to pi divided by 18. Okay, this is pi divided by 18 radians. Okay, so in your calculators, find sine of 10 degrees. Sine of 10 degrees happens to be 0.173, and if you were to calculate pi over 18, this happens to be equal to about 0.174. So you see, so 10 degrees is a good approximation, but as you lower the angle, this gets closer and closer. Okay, and that's something that we already know about the motion. So let's use this. Let's draw this system. Let's draw some forces acting on this object. Okay. Now here's the question: why does the object swing back? Okay. What are the forces acting on it? If you look at the forces, we have gravity pulling it down. This tension that is essentially keeping it in the circular path. Okay. And those are the two forces. And if you look at this, okay, the force that actually brings it towards the equilibrium position is simply a component of gravity. So this is the angle theta. At any angle theta, what we know is that this force, okay, if this is theta, is going to be equal to mg times sine of theta. So it is this component of gravity, this force, that will bring this object back to its equilibrium position. All right. Let us also call this arc length S. Okay, so what we know is that this force is equal to negative mg sine theta, and the reason we write the negative sign because it's a restoring force. It wants to bring it back to equilibrium. All right, but for small theta, such that sine theta is approximately equal to theta, we know that this restoring force becomes negative mg times theta. Okay, but if you look at this little picture, okay, of the arc length, the radius is L, the arc length is S, and if the angle is theta, then we know that the arc length is dependent on the angle theta in the following manner. Okay, so I can rewrite this as minus mg times S divided by L. Okay, now we ask, what is F equal to? And F is simply equal to m times a. So you know that ma equals negative mg over L times s. But a itself is the acceleration, so it happens to be negative g over L times s, where s is the distance traveled by the arc length rather. Okay, so s takes the role of x in this thing. So if we were to compare this with a equals negative omega square over x, we see that this motion, this equation, is nothing but that of a simple harmonic motion, simple harmonic oscillator. Okay, with omega equals square root g over L. And once you know omega, we know everything else. write down what t is. Pause the video, see if you can write t correctly. Okay, and I'll move on. T happens to be 2 pi over omega, which is 2 pi times square root L over G, and the frequency f is equal to 1 divided by t, which is 1 over 2 pi times square root G over L. Okay, now there's something interesting goes on. What we notice is that this time period is only dependent on the length of the string and the acceleration due to gravity. It is independent of the mass. T is independent of the mass. So if instead of a 1 kg block I put a 10 kg block and I do the same thing, okay, the time period is going to remain the same. It's not going to be affected. It is going to be affected on the length of the string, and it is also going to be affected by the acceleration due to gravity. So if you were to take, if you were to repeat the experiment on, say, moon, for instance, with the same length of the string, then the acceleration due to gravity will be different. Similarly, the frequency will change. Okay, so the lower the acceleration due to gravity, the longer the time period. Okay, the higher the acceleration due to gravity, the shorter the time period, and hence similarly the frequency will be higher the higher the acceleration. It will be lower the lower the acceleration. So if you were to say repeat this experiment, if you were to take a simple pendulum on the earth and measure the time period on the earth, on the surface of the earth, and if you were to repeat the same thing on an airplane, okay, you should expect a higher time period for the motion, okay, and at the same time a lower frequency on the airplane compared with what happens on the surface of the earth. Alright, so this is all the stuff that you need to know for a simple pendulum. So once again, it all starts with this approximation, the saying that making this statement that the motion is going to be simple harmonic only for small angle theta, such that sine of theta is approximately equal to theta, because in other cases it's not. In fact, the problem cannot be solved analytically when theta does not satisfy this condition. Alright, so that is it for the simple pendulum.